We now introduce our second speaker, Christopher Volek of Shopify.
Currently,
And he will be talking to us about redundant distributed queuing and Apache Kafka.
Thank you.
First question, who built it before Apache stole it?
Not LinkedIn. Yes, LinkedIn. Yeah. They didn't steal it. They were like given it. LinkedIn was like, please God, take this off our hands.
Yeah, that's usually what happens with Apache.
Yeah, Apache doesn't want anything. They just are willing to accept it. Okay, so this talk is going to be a little longer than I wanted it to, but as I was trying to cut pieces out, every piece I cut out made it a little bit harder to justify things later.
Just talk faster.
Oh, that's what I'm planning on doing. So the first half of the talk is not Kafka, and then the second half is Kafka. So I'm just going to try and get through the not Kafka parts so that you can know enough reasons why Kafka made the choices they did, because you know what they were competing against, sort of. It's not a competition, everyone always wins. All right. So we're going to start with queuing. So this is a queue. Basically, the reason, the problem space that we're in is that there's some stuff and you want to do it, but not now. Yeah, basically that's it. So let's say you're a web server and you've got requests coming in and you want to like do these computations, but like you're busy right now, so you want to have someone else do it, or you're a phone system, or you have this batch processing that you want to happen on like a daily schedule. Either way, you have something that you want to do, so one of the first things that people reach to is a queue. This here is a simple queue. It's like your normal CS level queue. Work goes on the back, and then things come off the front in this left to right world I live in. So basically, it's got like the FIFO properties that you expect out of a normal queue, being that the first thing in, this 1 is the first thing out. So if you add 1, 2, 3, 4, 1's the first thing that comes off. We're going to tear that apart real quick. There are also a bunch of words for it. I'm going to use all interchangeably. I've heard push and pull. There's queue and dequeue. There's enqueue and dequeue. There's produce and consume sometimes, even though it's a whole other thing. So just if I say something that sounds like I'm putting it on the back, I am, and if it sounds like I'm pulling it off the front, I'm doing that. Queue works super great. CS. Okay. The first problem though is that you've got a worker and they cannot keep up. You're pushing things into the queue faster than you can pull them off. That's when everything starts to fall apart. So you might have a concurrent queue. In this case, you've done a little bit more work to make your stuff thread safe, so that if A and B, these are workers by the way, want to both ask for work at around the same time, you're not giving them both work unit 1 or something stupid. Relatively easy to do, but at this point you have more than one worker pulling off of your queue. At this point already, we're not quite FIFO, depending on how you define it. The work is started in FIFO order, so we have A ask for number 1, it gets number 1. We have B ask for number 2, it gets number 2. Super cool. But they end in any order whatsoever, because 1 might hold on to this work unit for like 10 minutes, and B might be like, okay, then I did 2, then I did 3, then I did 4, then I did 5, now I'm idle, and whatever work 1 was doing isn't done yet. So they start in FIFO order, but at this point they end kind of whenever, and if that's important, you need to make sure that you're taking care of that. Concurrent queue. Oh, if there are questions, you can ask them, but again, I'm just going to be kind of speeding through this first part, so if they're not that important, just keep them to yourself. So,
Chris,
the problem with this...
question, why did you say that? And what are my feelings?
I wanted to establish an aggressive rapport with the audience. The biggest issue with that is my workers are not infallible. In fact, they often suck and they can die. So then you might throw some sort of committing queue into the works. So this one, the work is never actually taken. Well, not never, but so work unit 1 is, or worker A is like, I want to take some work, please. And what it does is it's not given an item off of the queue. Instead, it is given a lease to the first item on the queue. Or implementation details, we'll talk about in a second. And then the second item, B, gets a lease to number 2, and then the seed gets a lease to number 3, and now they all have it. What that allows them to do is if they die, like if C were to suddenly, or if B were to suddenly die right now, oh no, that's not what that's like, whatever. So A finishes its work. At this point, it commits the work, so now the item goes away, and A gets work unit number 4. So it's kind of like a queue, but things don't disappear until you're done with them. Now, if B were to suddenly die, the work unit number 2 goes back. It never actually left the queue, so it's still there, and something else can do it later. This changes the processing model from at most once processing, where the work is done at most 1 times, either 0 or 1. Because if the worker dies, it's done 0 times, and if it's done, and if the worker does not die, then it's done 1 time. This shifts it around to at least once, in which case you might do the work 1 time, because either it died and it got picked up again, or it did, not die, which is the hopeful case. Or it might do the work 100 times, because it picked up the work, it did the work, it put it in the database or whatever, and then it died in the trying to commit phase. So the work was done, but the queue doesn't know about that, and then it dies, and then the next worker picks it up, and it does the work again, and then it dies, and then the next one picks it up, and it does the work again. And so your work might get done 1,000,000 times, so we call it at least once, because whatever. Usually, at least once is better than at most once. It's rare that you put things into the queue that you don't actually want to happen. But sometimes you have to be careful if you know that you're doing that you write your work so that if it happens 100 times, that's not really a bad thing. So like some things, like if you're setting a user's name and you set their name 6 times in a row, like their name is still set, it's probably cool. But if you're transferring money from one account to another, you really don't want to do that multiple times. So you have to do work using identifiers or whatever, or something to make it idempotent so that if you do the work more than once, it doesn't do extra things that you don't want it to do. So as much as we were not quite FIFO before, we are now definitely not. So that's kind of fun. Because at this point, work unit 1 got started and then finished. Work unit 2 might have been started, but might not have. It's kind of hard to tell. Work unit 3 is in flight. It will probably be done soon, and then we'll start 2, maybe. So at this point, it still is like FIFO-ish. We start kind of towards the left, and we kind of move towards the right. But all bets are off on ordering, and if that's important to you, then you need to do extra work to make sure that you're not going to F that up. Like, for example, if over here a user decided to set their name to John, and then they're like, oh crap, my name's not John, it's Steve. Over here in work unit 2, well, okay, that's a bad example. Let's say they set it to John in 2, and then over in 4 they set it to Steve. At this point, we're about to set this to Steve, and then later come back and be like, oh, John, that's what it's supposed to be. And it's like, oh, undone all your stupid work. So again, if that's important, you need to be really careful that what you're doing is a thing, because you don't actually have a queue anymore. You just sort of do. The other problem is that this takes a lot of sort of complicated, well, it can take complicated bookkeeping, because, for example, you've got all these leases, and so now, rather than just pulling off the front, you have to be able to scan through from the front, looking like, oh, is this one allocated? It is? Damn, okay, is this one allocated? Okay, damn, okay, is this one allocated? Which is not one of those 2 queue operations that most people think of as a queue operation.
Can you not use a heap?
Yeah, you can. So yes, so you can do things. You can do that. Another thing you can do is you can use a double-ended queue, and you can pop off into a hash table over here that keeps track of all the in-flight work. And then this is still just a queue, except that later when one of your consumers dies, you pull it back off of the heap or off of the hash table, and then insert at the front of the queue. In which case your queue is still pretty pure, but now you've got this other data structure you're managing. It also gets a lot more complicated because now you have to start getting into philosophical questions like, what is death really? Because it might be that maybe this broker just stopped connecting to the. Oh, sorry. This is called a broker, by the way. This part with the queue in it. For now. So maybe this worker just stopped talking to us, so we assumed that they're dead and we gave their work back, but they're not actually dead. They finished the work and then they come back and they're like, okay, I did it now, but we've given it to somebody else. Hang on. We've given it to somebody else. So in this case, C finished its work, 3 went away, and now C was given 2 because it was the leftmost thing that wasn't allocated. So at this point, B might come back and be like, all right, I did 2, we're good now. In which case you have to tell it that it missed the boat. But otherwise, maybe these things aren't supposed to be talking to the broker constantly, so now you have a timeout, but like what if the work takes a really long time, like a legitimately long time? So you have to start deciding on like at which point do these leases start to be released, and then no matter what you're doing, you now have to have things that watch these leases to like see which ones are supposed to be reclaimed right now using whatever things that you're supposed to be doing. So not too bad, but that's fine. So this is great. The problem is that we fixed this whole redundant or broken workers thing. The next problem is that the brokers are broken because humans wrote those too. So pretty common solution here is to set up this time there's an N, redundant queue. So in this case we've got our broker, same way as we already had it. He does all the same things we just talked about, but there's this other broker up here that we don't actually talk to. And every time something gets added to this one, it gets added to that one, and every time, depending on your implementation, every time this one gets a lease, that one gets a lease or something like that. And this is basically just there to be a hot backup, so that if at any point this whole broker just dies, these workers can all go start talking to that guy. They've already got all the data, none of your data was lost, because again, you probably put things in the queue because you wanted it to happen. And everything is just kind of great. So we call this one the master and this one the slave. That's pretty common terminology. The biggest problem now is you've got the bookkeeping, not only the bookkeeping over here as to like what the leases are and how they work, but you also have the bookkeeping between these two nodes. So this one is telling this one all about the stuff that it's seeing. And the slave really only does stuff when the master dies. So you've got this whole, this thing has to be capable of being the master, right? It has to have all of the performance characteristics and everything you need out of your queues, because if this thing is garbage and this one dies, everyone goes and floods the garbage and it dies as well, which is bad. So it has to be there, but you really hope you don't need it. It's like insurance, right? You need it, but you don't want to. Most of the time it's just dead weight. And then you also have questions about, like, remember all these leases I talked about? So if you were doing your liveliness, as in like, well, these workers are still talking to me, you now start having the problems where like the workers were never talking to this one. So now you have to have A be able to go over to your slave and be like, hey, the master's dead, so I'm talking to you now. By the way, I'm A, and I am currently in flight on this thing number 1, so please don't reclaim it. Or like what happens if someone doesn't make a transfer. Anyway, so there's that kind of stuff you have to work with. But basically this is fine. At this point you can tolerate failures on the workers and on the brokers. Everything is lovely that way. Next thing that can go wrong is that the brokers themselves can't keep up. You have too much work that's just happening all the time. You can have millions of workers, so that's not really a problem because they all just pull from the queue. Every worker you add adds more overhead to the actual broker, but like whatever. So, but at some point, either work is coming into the brokers too fast, or there are too many workers. Either way, the brokers themselves are in trouble. So then you can shard the queue. So now you have, these are all the same things I just talked about. You just have more of them. They're each doing their own stuff. They've all got their own workers. And when you publish, you produce to one of these queues. A given work unit only goes into one queue. You don't give it to all of them because that would defeat the whole point. And so now you've spread your work out over multiple brokers. Each of these brokers can have multiple workers, and the whole thing just kind of, you get your work done and it's fast, and if any one of them fails, it fails over, and all that magic garbage. Totally cool. Oh, I should mention, in terms of failover, there are also non-broken reasons why you might want to have two. Like if there's some, for example, like a security update, if we're in practical land, you might want to be able to run the update on the slave and then do a switch over and then do an update. Oh, that's weird. And then do an update on the thing that was previously master in order to, like, you know, get your update out without having to bring a bunch of stuff down and potentially lose data or lose time or whatever. So it's not just things that are broken why you might want to have two. And so now we have 6, but they do different things.
If you have to do a security update, isn't something broken?
Yeah, okay, fine. Yeah, sure. Or, yeah. I mean, different kind of broken, I guess, yeah. Yeah, so at this point, you might have noticed we're not even trying to be FIFO. Because originally, when we were doing these leasy ones, we still had the guarantee that like we're probably going to try to attempt the first thing that got put into the queue before it fails, and then we try other stuff instead. So like the first try starts in FIFO order, but anything else can happen. But with a sharded queue, we might put work unit 15 over here. Let's not pick that. Work unit 14 over here and work unit 15 over here. This queue might be really, really busy because of bad luck, and this one is really, really easy. So we're just going to scoop all the way through here. We're going to pick up number 15 in like 2 seconds, and we're going to start working on it. And it's going to be 20 minutes before we ever even look at work unit 14. So at this point, it's, again, within a shard, it's FIFO-esque. But amongst the whole set of things, there's not really a lot of FIFO going on. So, kind of like a queue. Queues. Okay. Okay. Actually, this talk might not be as long as I wanted it to, or as I was afraid it was going to be. Cool. So that's queues. This system back here totally works. We've been doing this for years. It's kind of like the way that things are done. It is not Kafka. It's just there, and it's great. But let's talk about Kafka because it's popular these days. Okay, so Kafka does a couple of things. I'm going to go through them sort of one at a time. Oh, does anyone have any questions about queuing before we move on to Kafka? Yeah?
Does this setup not assume that, for example, a given task not that necessarily is a prerequisite, a previous one is a prerequisite, but that maybe the speed, for example, 15, if 12 is done before 15 is started, then 15 might go faster, or 15 needs 12. Nothing like that is assumed in this, right? If 15 needs 12, then you would produce a 15 prime, which includes 12 in it.
Oh yeah, so yes, there are a ton of more complicated features that most queuing systems will build into things like dependency management or some sort of atomicity probably. This is a very kind of an overview. There are definitely features that modern successful brokers add in to kind of keep track of a lot of that for you. And at the very worst, you can write a lot of that yourself if you're willing to spend time on it. Like you could have your work unit 15 start with some sort of prerequisite check, and it says that it doesn't happen, so it throws a failure itself and it's like, try me again later, something is bad. There are definitely features that many brokers give you as part of their suite that I haven't quite touched on, but they're in there. Yeah.
Workers. So these ones seem to each belong to a broker.
Yeah.
Is it a bad idea, or
to have it
workers that read all the brokers?
It depends. So one of the things is if the problem is just that your data is not being produced fast enough, then sharding this way can help. But if the problem is that you have a million brokers and the overhead of a million concurrent brokers if you have a million workers and the overhead of a million workers is bad on an individual broker, then having a million workers that are all bringing down 3 brokers isn't helping anyone. And even if you have a pool of workers that's connecting to multiple brokers, each worker still has to decide, okay, am I going to go pull from this queue or from that queue right now? On a given moment, they have to decide who they're going to service the packet request from first. So you can still end up with starvation and weird stuff. I don't know. It depends on stuff, I guess. It's system administration stuff. Yeah.
If I have only one worker,
yeah,
but all of these brokers for redundancy reasons, etc.,
yeah,
I get FIFO back, right?
If we're talking about this, then yes. If we're talking about this, then not necessarily. necessarily. Because of the thing, if I was round-robining through my brokers in exactly the order that my producer was round-robining through my brokers, then yes. Because I would specifically pick up, first I would pick up work unit 1, and then I would pick up work unit 2, and then I would pick up work unit 3. But if I was doing anything else, or if I was even just mismatched with my producer, if I was going in this direction, then I would pick up 1, 3, 2, 4, 6, 5. Or if I picked up 1 and then 4 because oopsie network something, and then 3 over here. So not necessarily, but potentially, if I was careful. Any other questions about queues that I might be able to answer?
Why is it pronounced Curelet?
English. Mostly English. I think when they were originally created, it was Quewe and like the de Quewe, but something just happened in the middle. There's a vowel shift. Okay, Kafka. So Kafka, I'm going to start off by talking about what they did differently. And it's going to seem for most of the rest of the talk like it doesn't solve the problem at all. Just kind of push that down, and we'll get there by the end, kind of. Because that's how it goes. So the very first thing that Kafka did was it was like, queues are stupid in our queuing system. So let's use an append-only log. So this is a different data structure. It is no longer a queue. Where queues had push on the front and pull off, or push on the, whatever, this side and pull off of that side. The append-only log has push onto this side, read from anywhere that I want in the middle. Yeah, so that's basically it, Kafka. No. But that's kind of the core of their change, was they decided queues are hard or whatever, and so we're going to do logs instead. So again, you can read anywhere. At this point, we don't really have the word queue anymore because it's not a queue. It's not even pretending to be a queue yet. So we call these topics in Kafka land. So a thing that you put multiple events into is called a topic. So you might have a topic for transactions or whatever. So this is great. I can just push work in here, and my worker can just kind of go at their leisure and just decide wherever the hell they want to read. They can just do that, which is something. So the real problem is, how do you keep track of where in the log you should be reading, right? You have to be reading from somewhere. Where do you read from? So the answer is that Kafka, this is going to be a theme coming on. Kafka put a lot of the worker onto a lot of the bookkeeping and effort into the consumer. They said, I don't care where you read from. You can ask me to be read from anywhere. You keep track of where you should be reading from. So it's up to the consumer to decide where the hell they should be reading. And then they just ask Kafka, hi, I'd like, offset, by the way, is the term they use for like where I'm reading from. So they just be like, yeah, I want offsets 1 and 2. And it's like, sure, here they are. And then you go away. And then later you come back and say, okay, since I've got 2, I'd like 3 and 4. It's like, sure, here they are, here you go. And then 5 goes in at the back still. So this is cool. Kafka has ways, they have like recommendations that they can use to help you keep track if you want their help. Or its help. Yeah. But you don't have to use it. You can do whatever the hell you want. You can write to a file on disk, you can keep it in memory, it's up to you. One of the cool things about that, though, is it allows you to do at most once processing, because you can say, I would like to read item number 1, and then you immediately store in wherever it is that you're storing this stuff that you have read item number 1. And then you get item number 1, you go, and you immediately crash, but like that's your problem. And then when you start up again, you ask for the thing that came after 1, and you get number 2. Totally cool. But if you want at least once, you can do sort of the same thing as you did in the last one. You get item number 1, and then you say, okay, cool, now that I've done all the work and I've saved it in the database, I'm going to save into whatever it is I'm using to persist this stuff that I have done number 1, and then if you die before you can do that, you'll start up and you'll do number 1 again. Also cool. And it's up to the consumer to decide how they want to handle that. And in fact, you can actually do exactly once processing in some situations, which is sort of a holy grail of sorts. So like, let's say that you're doing some sort of a running average of, average transactions per day or whatever. So you've got all your transactions in this Kuewe. Actually, it's a log. It's a log. Fuck. Anyway, so you've got all your transactions in this log. And what you can do is you can store your offset and your rolling average in the database right next to one another. So you can consume number one, and then you can be like, okay, my average so far is whatever the hell was in number one, and you save the offset of one and the rolling transaction value into the database in a database transaction. And if it succeeds, then you have the average so far and the offset of one. And if it fails, then you have no data so far and no offset. And then you can roll up to 3, and at this point, if you process number 3 and you go to save it in the database and you crash, then you still have offset 2 in your database and the number you got when you ran after offset number 2. So you're just going to do 3 again, but it's not a problem because you're not basing it off that data anymore. They're kept in sync, which is really hard to do when the broker's responsible for this sort of thing. But because the worker can do it, then they can do whatever the hell they want, and that's one of the things they might want to do. Yeah, so this is great. The worker can just kind of go through here and just kind of do whatever it is that they want, and it just kind of works great. If there's a single worker and I've got one log, it's just delightful. But sometimes I might want multiple logs, or multiple consumers, actually. We'll get to multiple logs later. I might want multiple consumers, and at this level, if I were to spin up number B over here, it would just read all the same data again, because this one was like keeping track of its state, and then B comes on and it just starts reading its own stuff. And now I have my workers all consuming the same data, which is not really what I'm using a queue for.
Unless they synchronize their offsets in some other...
Yes. So in theory, yes, I could have A doing this and it would be passing up to here, and then like B would whatever. But at that point, yeah. So I'm going to take a quick aside though, because what we've accidentally stumbled on is PubSub, which kind of was crappy with the queuing system, because at this point, if I have 2 different kinds of workers who are both interested in the same data, like let's say this was a log of transactions, and like this person up here was doing averages, and this person down here was like putting widgets in dashboards or something, you might actually want every single transaction to go to both of these, because like you're doing 2 different things with them. And by having this drawback, we've accidentally found this like delightful thing. So in this case, these consumers are storing their offsets differently from these ones, and so they can both consume through all the data, they can both keep track of where they are, and they can both do whatever the hell they want, and they'll both get all the data, which might just be swell. If I wanted to do that with the queuing system before, because the whole point of it is that it takes the data and consumes it, what you have to do is either you have to have a producer that pushes into 2 or more different Quewewe's, or you have some sort of like dispatcher worker unit, so you put it onto like the master queue, and the master queue pulls it off and is like, oh, this is a transaction. In that case, it goes to this other queue, and to this other queue, and to this other queue. And in fact, some brokers actually have that built in, so you can say if you publish to this sort of virtual queue, what I know how to dispatch that to these other 7 queues. But either way, someone at some point needs to know who the consumers of this data are going to be, so that they can put it in the appropriate queues, so that each of them can consume the data exactly once. Whereas with Kafka, you drop it into this log, the different consumers can all read it, and I only had to store it once. And what's even better is that the consumers are all cheap. They can spin up, I can just spin up 100 of these things, and they all just ask for different bits of the data, and the actual broker doesn't care, because you just asked me for a number and I gave it to you. I don't know if you're the same person or a different person. It's not important to me. So if a consumer pops up later that I never expected and just asks for the data, I just give it to them and now they have it, and no one needs to know. It's actually sort of cool. So for example, there's a tool called Kafka Cat, to get, again, back into the practical side, which is sort of like tail or cat, depending on how you're using it. Probably it was named cat for the cat way, but it also does taily stuff. That basically you can point it at a topic and say, please give me the data, and it just like dumps it out to standard out. With a queue, this is the worst thing you could ever possibly do, because you put the work in there so that it would get done, but you just consumed it all and threw it onto the screen. Like, that work's never going to happen now, which is the worst. So there are things that your brokers can do, like they can have like a peak function, but now you're just implementing an append-only log in your queue, because now you have to have a queue that supports reading random chunks without consuming it. And you've built all this like machinery to keep the queue, this sparsy queue in place. But then you were just linearly scanning through it for debugging reasons. Or you can have a debugging queue, but then that grows exponentially. It's terrible. Whereas again, because Kafka doesn't actually care about what the consumers are doing, you can just spin up a command line program, dump the data out, and then like do it again from the start, which is actually kind of delightful. So this is all great. I've convinced you all that this is actually what we wanted all along, and we don't need queues, we just have consumer groups and we're done.
You didn't say consumer group yet.
Oh yeah, by the way, these are called consumer groups. These different shapes I've done here to represent that different consumer groups get all the data as each other pops up. So unfortunately though, sometimes we actually want queues. And Kafka was like, oh, that's neat, I don't do those. So instead they hacked around it by partitioning. So append-only logs, at no point did they ever try, or whatever. It appears as though at no point did they try to actually make the append-only log work queuely. Instead what they said is, they said, great, well what if we just had n append-only logs and each consumer was like in charge of one of them? Or each one of them had exactly one consumer from each consumer group specifically. And that's basically like the whole solution is, so this one, for example, I've got a single consumer here that is pulling from both of these partitions, which are each an independent append-only log. So in that case, it was like the thing we were talking about a second ago with the worker pulling from multiple brokers. It'll pull some from over here, it'll pull some from over here, it'll keep track of the offsets separately, everything is cool. And then this consumer group has two workers. It pulls, one of them is in charge of this one and one of them is in charge of that one. And Kafka's basic thing that it does not want you to ever break is that it never wants a partition to have more than one consumer from the same consumer group, because it doesn't do any sort of synchronization with offsets. It says, this one is all yours. You can keep track of it however you want. You can store it in disk, you can store it in the database, whatever. You can even, because the Kafka thing allows you to request blocks, so which is actually what I've been drawing this whole time, is I can say I want 1 through 5, and then I'll work on them in my own time, and I'll commit them however I like, and then I'll pick up another block later. And you can do that safely because you know that while you're in there, no one else from your consumer group is in this partition. It's all you, all your own, do whatever you want. So this works in practice. It is not elegant, and it is definitely not a queue, but it kind of works out like one.
It just means that you have to make server-side changes every time you want to increase your parallelization.
Yes. So the main thing here is that because you can have multiple partitions per consumer, but you can only have one consumer per partition from a given consumer group. Which means that if you have 15 partitions, you can never have more than 15 workers from a given partition group. You just have to be okay with that. Now, because you can do this sort of stuff, you can sort of front load, so you can decide, I'm going to have 30 partitions, and I'm going to have 10 workers to start out with, and each of them will have 3 partitions that are theirs, because the volume isn't that high, and they can all sort of pull from it. There's a little more overhead when you do that than that might be necessary, but it means that you don't have to make server changes later when you make twice as many things, and now you have 15 consumers that each have 2 partitions or whatever. But if at some point 30 workers is not keeping up, you do have to go redistribute your data, which is one of the downsides. It's not magic. Nothing's a silver bullet. But you can scale your partitions independently per topic. So if you have multiple topics in your queue, you can be like, this one is really high volume, I'm going to have 15 partitions. This one, something gets written to once or twice a day, I'll have 2. Because 2 workers, or at most, should be able to keep up. So that's kind of nice, I guess. The producer is in charge of which partition they produce to. Oh, by the way, if you haven't noticed, there's kind of a reference back to, remember when we did sharding back in the good days? It's kind of like that, but at a much smaller scale. They kind of flipped it upside down. Anyway, so it's up to the producer to decide where they produce to. You can produce kind of round-robinly if you want. If you want more smarts, in theory, you could produce in some sort of load-balancing way. If you have that kind of data, you can produce to the one that is kind of has the least data. Or, to get on a quick little aside, because I've got time, remember with FIFOs how like if you had multiple data that was like really important, the FIFO-ness might be lost? Because you only have one consumer going through a given partition, it's a FIFO, like an actual FIFO for realsies. So what you can do, if you're willing to accept the consequences, is you can do things like, every user, like let's say I wanted to set a user's name. I could basically just hash the user's name. That would decide which partition it goes into. And so then I know that all of the updates about a particular user are well ordered in my given partition, so I know I'm going to be going through that user's updates in FIFO order, because the rest of the users I don't really care about. You can do that. It works really great. The only problem is that if some of your users are more active than the others, or if your hash function is garbage, you can end up with a queue that's really, really, really big, and the other ones are all kind of empty. Which can be a problem, especially because the partitions are kind of a cap on your workers. One of the other drawbacks is if one of your workers is overworked and you're already at one worker per partition, there isn't really anything you can do to help them. You just kind of have to like, oh, that sucks for you. I'll try to redirect new data in the future down to other partitions. But like, I can't start up another worker to help you out because it's only your partition. Yeah?
So going back to your name example, if you were kind of skirting those between partitions, there's no ordering between partitions.
No ordering between, no, yeah. So like our shards, each of our partitions is completely 100% distinct from one another. There is nothing in Kafka to do any sort of correlation between partitions. And if that's okay, if you're just shooting random events into the log, then that's totally fine. But yes, within a partition there is an ordering implied by the fact that they only append at the end. Whether you want it or not is up to the producer and I guess the consumer a little bit, but it's there. Like in theory, you could build a consumer that like daisy skips one at a time and then zips back and does it again because they can technically ask for whatever they want, but like that's bullshit. Just don't do that. Yeah. Okay. So this alone is mostly Kafka. The rest of the stuff I'm going to be talking about is like nice things that it also does to get back to the big complicated looking diagram. But really, this is it. You have an append-only log. You split it between your workers into into petitions, and then that's what it does. And so all of the queue-ishness that it gets from having these things that I just talked about. Yeah.
So if it's append-only log, what happens when you run out of log?
So there's a couple things. So Kafka, you can keep logs by a number of different metrics. Kind of like log rotation, actually. So basically, it can truncate from the front. If there's a certain number of events in the log, you can be like, this thing should only get to 2,000. You can do space if your logs are differently sized, or your individual messages are differently sized. You can be like, it should never exceed 50 gigs or whatever. You can do time. You can like keep the last week's worth of logs if you have enough disk space to burn. And technically, I wasn't going to talk about this, but since you kind of brought it up, it also supports a thing called log compaction in newer versions, which means that if you give each of your events a key, like a primary key, then what you can do is you can actually throw out updates that have a later message with that same key. So for example, if these were username updates, again, Kafka can actually be like, oh look, this user changed it. I don't know why users are changing their names so often. You've got to, anyway. Okay, let's say it's a balance. You've got balances. You're computing balances, and the balances change a lot. So you can use the user's ID as a key, and so when it compacts, what it does is it goes through and it keeps the last update to a particular user's balance. So then your log gets shorter at the front, but you still have like the most tasty big data. There's nothing about that between partitions. You kind of have to partition your producers at that point, but or just not care. So yeah, it gets shortened, but that happens in like a rolling cycle later. It's not part of the reading process. It's completely divorced from consumption. Because again, Kafka doesn't know what you have and have not consumed. I'm going to stick with it. Kafka doesn't know what you've consumed. It's all up to the consumers. English. So, clustering.
More alphabets.
Hmm?
More alphabets.
Oh yeah, because I can't use the same things more than once. So that kind of got us our queue, but that was now our queue-ish thing. But that was only one, and so you can still run into the problems where like, what happens if my broker dies or whatever. So Kafka does clustering rather than sharding. So it's a modern clustered thing. So basically what happens is you have these brokers, which I've labeled Greekly. And in this case, I have a topic with 8 partitions in it. And so what happens is I create an 8 partition topic. And it goes, cool, I'll put like 1 and 6 over here. I'll put 2 and 7 over there. 3 and 8 will live over here. And 4 and 5 will live down here somewhere. And so now when I'm producing, my producers, I don't have this arrow, but when producers produce, they're like, okay, I decided I want to produce to partition 7 through whatever means. So I tell broker beta that I want something on producer 7, and it's kind of in charge of that. And the consumers who are consuming from partition 7 talk to beta, and they don't talk to any of the rest of these. So this is a way of just kind of distributing the load, which is kind of nice. And it also means that if I bring up, if my brokers are having sort of a struggle, I can bring up 3 more brokers, I can redistribute my partitions, and now their load on all of them kind of goes down. But at no point are any of them doing nothing, they're all doing something, they're just not all doing the same thing. So that's kind of delightful. And part of the reason I can do, well, anyway, whatever, I can do that with queues, I guess. Yep. So then we wanted redundancy, because we didn't want our brokers to die. And so like back here, if broker alpha went down for maintenance or whatever, partitions 1 and 6 are just effed. They're, no one can produce to them, no one can consume from them. The data might be gone if the disk failed. Bad. So we added redundancy for that. I say we, I'm not a Kafka developer, but I'm pretending to be one for the purpose of the presentation apparently. So Kafka added redundancy, but because it's already clustered, basically it just throws the redundant things back into the cluster. So each of these each of these partitions gets its own sort of master-slave thing going on. So this has a replicancy of 2, which means each partition has 2 copies, the primary one and the backup one. You can scale that up or down on a per topic basis. So if some data is mission critical, you could have 5 replicas, which means every single broker must have a copy of this message, but for like logs, 2 is maybe too much, because if you just miss them, then whatever. Anyway. But because we have a cluster, we've just kind of thrown them all into the cluster, so with the only rule being that we don't really want too much correlation between them all. So we're like, okay, partition 1 lives on alpha, but then like beta also has the backup for partition 1, so the data that goes into partition 1 gets sent over from alpha to beta, and then, but partition 6 is over here. Where did I put that one? Down here. So it's all just kind of there, and it's all clustered and distributed. So again, I have redundancy, but because it's per topic, per partition, again, none of my brokers are idle. They're all doing something, and if one of my brokers were to die, like this one, in this case, we've given 3 is now primary down here on delta, and 8 is down here on epsilon. And the load on sort of all of the brokers has increased by like 1 over n minus 1, rather than going from 0 to 100 on a thing that was currently doing nothing. The load has just sort of gone up a little bit on all the rest of them. So if you're writing your brokers like really close to the edge, you could theoretically have this whole cascading failure thing where they're all like, oh my god, and then like the one goes down and just kind of brings them all down. So don't do that. But in general, your brokers are all doing something. At this point, when a broker goes down, the whole cluster elects a controller, which is essentially like a temporary dictator. Because having, you could think of it as doing a little election on each of the like remaining partitions, being like, hey, I'd like to take number 3, and it's like, oh, I'm so busy. But that's inefficient. So instead what it does is one of the remaining nodes gets told, divvy this up, and it just goes in, it's like, you're getting 3, you're getting 8, and we're all good now, done. Which is kind of fun. And then at some point, it might come back, in which case we kind of end up back in this state again over here. it might not be exactly like this because by then it's just a new node coming in. So, for example, if we look over here, like they all sort of have 2. So probably this one would just keep 3, and this one might get 2 back or something, or 8. I don't know, or it might just anyway. So like it would kind of like re-elect and redistribute a little bit. It might not go exactly back to how it was because it's just trying to kind of adapt to how things are. And obviously, if you bring a new node in while this one's down, you can redistribute again if you want to. Yeah, that is most of the. That's it. That's the technical parts. That's everything. I have some I have some thoughts on why, but if you have questions before that, we can do that.
Sorry, there's one. Right. How did the consumers learn that a different cluster has taken over the job of being the primary for a partition that they're interested in?
Yeah. So basically, the clustering reasons. So every time there is a change to the broker set, the consumers are notified, even if it's not directly relevant to them. So for example, if I'm consuming number 2, and I was consuming it from here, or screw that. If I'm consuming number 2, and then like alpha goes down, I get told, okay, these partitions are now these things, and so everyone kind of knows what the whole state of things is, and especially they know what all the other brokers are. So then if beta were to go down, or if the gamma were to go down, I would know who all the other brokers are, which at least gives me a way to connect to one of the other brokers and be like, hey guys, who has partition 2 right now? And he'd be like, oh, beta has partition 2. It's like, okay, cool, thank you. And then it like goes over and talks to beta. And then beta will update it from now on what's going on. So there is a kind of metadata stream going back and forth between the brokers if they choose to. And in an initial state, you start up the brokers with the consumers with a list of seed brokers, and then it kind of adapts from there. So in theory, you might even start up your consumers with this set, and if you're unlucky enough to pick gamma the first time, you're like, oh, okay, that broker doesn't seem to be doing anything. Let's pick one of the other ones from my list and see what's going on right now. Yeah?
You can also use proxies.
But
then you have the singles.
Yeah, like, yeah. So this is important because I'm fighting with it at work right now. One of the things is that because the brokers have ownership over things, you can totally use proxies, but you cannot use a load balancer that sits on top of all of them. It is very important to the protocol that you're talking to who you think you are. So you can't just have a load balancer up here that will just like round robin connect you to whoever the hell you want. You have to be able to talk to beta, because beta has number 2, and that's who you talk to for number 2. If you get routed to alpha, not only does alpha not the leader on number 2, but alpha doesn't have number 2 at all. They don't even have a replica of number 2. They don't have that data. So you could set up like a proxy on top of each of these that is like, and then like this is the beta, and it only ever points at beta, but sometimes beta moves. But you cannot load balance the whole cluster. You have to be able to individually address cluster elements. Yeah. Other things before I go into why? Yeah.
Isn't Zookeeper often used in this?
Yes. They're moving. God damn it! They're moving away from it. So internally, there's a thing called Zookeeper. It's essentially a toolkit for doing consensus. It's super cool if that's what you want to do. Otherwise, don't use it. And so internally, Kafka uses Zookeeper's atoms to do service discovery with itself. That's where Kafka keeps track of who the brokers are for given things. It's how they keep track of like who's the leader for stuff, who else is in the group. So it uses Zookeeper extensively. Pre-Kafka 09, Zookeeper was also how most brokers or consumers were recommended to keep track of their state if they didn't have a good reason not to. And in fact, Zookeeper was who they talked to if they wanted to find out who a given broker was. They would, rather than talking to Kafka, they would talk to Zookeeper. They would ask Zookeeper, hey, what are the Kafka brokers right now? It would tell them what Kafka has kind of self-elected, and then it would use that to figure out who the brokers are and what they're responsible for. Post 09, Kafka still uses Zookeeper extensively for its internal management, but they've moved it to the point of being an internal only implementation detail. And so the Kafka consumers on modern Kafka talk to the brokers, they get seated with the brokers, and the brokers exchange that information with the consumers. And the fact that the brokers happen to use Zookeeper for how they got to that data in the first place is mostly kept hidden from the consumers. Yeah?
Doesn't that make it harder to add a new broker?
Sort of, not necessarily. It's harder to add a new broker in that you have to stop all of the existing workers, or you have to tell them and then like start them with the new seed list, or like they will auto discover because Kafka will be like, hey consumer, did you know there's a new broker over here? And if the consumer wants to remember that, they can. So like a little bit, but
so Kafka will advertise the new consumers
over
its own protocol.
Yeah. I think the main reason they did that is so that if you're in a situation where you've got like a firewall, you don't have to expose Zookeeper outside the firewall. You can talk directly to Kafka, and Kafka can talk to Zookeeper, but you don't have to be able to see Zookeeper to use Kafka. And also, you're in a situation where if you wanted to use Kafka, you had to pull in two libraries that are completely distinct and be like, first I use Zookeeper to talk to these things, and then that gives me Kafka details I use to Kafka over here. So they just kind of consolidated. Maybe in the future they're even planning on moving away from Zookeeper, or like, whatever, I don't know. It's not my thing. But yes, Zookeeper was involved, it's still involved, but it doesn't look like it anymore.
Why don't you know the roadmap if you're a Kafka developer?
Because in preparing for this role, I did not research because I'm a bad actor. Any other quick questions before I get to some of the advantages and then wrap up with more questions? Cool. So, this is not a queue. It's queue-like, and it kind of does some queue-y things. But it's not a queue. So the question is, and also the other one works and has been working for a while. So what are some of the reasons? Oh, and by the way, again, Kafka's not a magic bullet, silver bullet. It doesn't solve all your problems. It doesn't blend your food. It is what it is, and it has some advantages, but like it's not better at everything all the time. So the first thing that it's better at is it's a little bit more resource efficient. Back here, when we're talking about these append-only logs, Kafka represents these as literally a file on disk. It takes the data in from the producers, it stores it on disk, and it sends it out to the consumers in the same format, specifically so that it can get the data from the producer and just dump it into the OS disk cache and be like, you write it to disk. And then it just stops, it just walks away, it doesn't care. And then when a producer asks for a particular, or a consumer asks for a particular range, there's a Linux syscall which pulls a file out of the file system and streams it out to disk. That's like a single syscall, and it uses that heavily because it means that rather than having to be like, oh, let me go find that for you, and then I, the broker, read it from the file system into my memory, and then I stream the memory out to a buffer, and then the buffer goes out to the network. I just tell the operating system, hey, send that part of that file to that guy, and then I just leave. My job is done. They'll get the data. The OS will figure it all out. The OS already has a bunch of caching and page caches and stuff that make it efficient. I just had to say, I just put it on disk and then I read it back out again. It's super easy. And I lean on the OS for doing all the smarts. Whereas with a queue, I have to keep pointers potentially. If I'm doing a heap, I have to move stuff around. This page fell out of the page. I have to manage that so that I can kind of keep all the stuff, super whatever. PubSub is dirt cheap. Again, I just store the data once on disk, and so if I have a lot of different kinds of consumers, I don't have to have different queues. And again, my producers don't have to care about who the consumers are. They can all just operate independently. Consumers are cheap, so I can spin them up without it being a problem. There's almost no overhead to multiple consumers, except that there are more people reading. The brokers divide the load, so I can spin up more or fewer brokers without having to be like, okay, well, if I'm not at if I'm just going to make it so that all of my really expensive machines drop down to 25%, is it, maybe I'll wait till I get a little closer to 100% and then I can like add a new broker to drop it to 50 or something. Whereas with Kafka, it's like, it's getting a little high, I'll just add in one more broker, everyone's load will drop by 1/n and we'll just kind of be okay now. And if one of them goes down, we just sort of like figure it all out together, which is kind of fun. So in that way, it sort of scales kind of cleanly. Again, there are some shittinesses. So for example, if I spin up new brokers, it's not, by design, it's not actually like super elastic. If I spin up new brokers, it doesn't just immediately start throwing my partitions around because maybe I don't want it to do that. I can ask it to do that, but one of the other things it can do with its whole scheduling thing is if I throw up a new broker, it can sit there idle. And then when I create new topics or new partitions, I'll schedule them over there on that new broker because it's really vacant, and that's a good place for me to put some load. And so like I can end up in a situation where like most of the old topics are on mostly these brokers, and a bunch of the new topics are on kind of those brokers, and there's some cross between them because I don't want it to be like too incestuous. But I can just kind of let the routing kind of take that up for me. Topics scale independently, which is kind of fun. So again, if I have a high volume, low importance topic, I can say this one has many partitions for parallelism, but low replication factor because I don't really give a shit. Whereas this one, I can have a high replication factor, but it only gets written to from time to time. So there's like 5 partitions, but they're on 5 different nodes each. In which case I might end up with like 15 of those and 25 of those, even though like whatever. And I can make those decisions on a topic by topic basis, or I can even change them after the fact. It puts a lot of the control in the producers and the consumers. So the producer, so I talked about how the consumers can decide what kind of consumption they want, right? Whether they want exactly once or at most once or at least once. The producers also can decide how important their data is, so they can either like fire and forget and say, here's an event, do or whatever, and I just like stop caring and I move on to the next one. Or I can ask Kafka, like, could you please tell me when you've committed this to disk, so that I know that it'll only go away if like you go away. Or I can even tell it, could you please tell me when you and all of your replicants can commit this to disk, so I know that it only goes away if there's like a data losing catastrophe. And the producer can decide per message which one they want to use, because it's a produce level option. They can be like, oh, this guy sucks, I don't care about his data, but this one's really important. Retention. If you wanted to do some sort of retention, or if you wanted to store stuff on disk in case of a failure, queues can almost all queues that are worth their salt can do some sort of disk saving for persistent reasons. But as much as it was complicated to do all of the bookkeeping when you've got like a queue in memory, serializing it to disk is even more of like a sore point, because now you've got all these files and you're managing them here, and then you push it to disk, but that's really slow. And by the time you push it to disk, you've already popped it out of your queue, and you're like, fuck! And then you have to like go and like get rid of it. And like, whereas Kafka being an append-only log, it was always a file. Like it was, whether you wanted it to be or not, it was a file. And so if the data gets killed and starts up again, sure, whatever. Like, and it's if the process dies, in a lot of cases, Kafka didn't even have a buffer. It used the OS's buffer. It just wrote, and then like it's up to the operating system to decide what to do with the buffer now. So that's kind of nice. It's also the case that consumers, because I'm doing retention, you can consider it a data store and not just a message passing system. And so a lot of the time, for example, consumers might start up at the back and run to the front, and you're like, oh shit, I have a bug. And you like, never mind, rewind, and you go back to the back and you like roll it up to the front again, and you're like, no, it's still effed. And you like do it again, and you just kind of like run it against the actual data 100 times, and no one actually cares. And then when you get to the end, you're like, this is great. And then even later, you realize like these numbers are looking a little weird. So like you throw it out, and you go all the way back to the start again with your new algorithm, you run it again, which is something that a queue just absolutely does not do. And the other thing is batch processing, if that's a thing you want to do, because again, the data is going to be saved either way. If you have a process, if you have a log that for some reason you want to process nightly rather than as it comes in, you can just start up once per night. You remember your consumer, your offset from last time, and you read up to the front, and then you save your offset, and you go to sleep again, and you don't start up again for another day. Whereas with a queue, that can be like the worst case scenario, because now your log just grows all day, because you're like, oh my god, why is no one reading this goddamn log? This goddamn queue, sorry. Whereas with Kafka, it was going to store the data anyway. Having no consumers is actually sort of like the best case scenario, because I put all the data on disk and then no one asked for it, so I didn't have to read it back out to them, which is just delightful. And again, because the consumer's responsible for their own thing, I don't have to worry about like this consumer that wakes up once per day and runs through all the data. I don't have to ask like, are they dead? It's like, no, they're in charge of deciding if they're dead, and they've decided it's totally cool that they run once per day. And again, the biggest disadvantage is that by splitting up my partitions at the front, like at the small scale rather than the big scale, I start running into the grocery store queue problem, which is that if this is the thing I already kind of alluded to, if one of my workers is really, really full and the others are all idle, that just sucks. And there isn't a Kafka way to solve that problem. I can't bring up more workers. I can't like redistribute items from one partition to another. They're in the log and they're just behind. Whereas with a queue, even though it gets much more complicated, until you get to sharding, you still should never end up with idle workers while other workers are really busy. But with Kafka, because you partitioned early, you could end up with more workers that are doing nothing and one worker that's really busy, if you're unlucky or whatever. In practice, if all of your workers are roughly able to keep up, the lines are always almost empty. So like it can work, but and does work. But there are definitely worst case scenarios that you absolutely could run face first into, and they just suck. It's a little bit more complicated to set up than a simple queue. Part of the reason why I spent the first half of the talk talking about the different levels of queuing is because that's really what Kafka is striking against. It's striking against the like sharded, replicated, all the things redundant queue. If you want a simple queue, it takes like 2 seconds to spin one up, and you just like have one now. I mean, you can write it with a linked list if you absolutely had to in memory. Kafka is not that. It's this whole clustered-y, self-discovering, healing machine. So I would say that it's possible that Kafka is as easy to set up as that huge machine of queuing that I described at the end there. But it's certainly, if that's not what you need right now, it will feel like you're doing a little bit more work to set it up than you might have otherwise had to do. Because I mean, it's not that bad, but it feels more complicated. There's more moving parts, and it also uses a lot of disk. You have to, because if you were storing data for a week, you need to have enough disk to store data for a week on all of your topics. I mean, or at least all of the topics that end up on a given broker. It also uses a lot of memory, but every broker uses a lot of memory, because if you're doing queuing not in memory, you're going to have a bad time. So Kafka uses a lot of memory just to like hold disk cache. But again, with a lot of brokers, you might think, oh, I only need like 2 gigs of data, because like most of the time my workers will be keeping up, and like I only have to store stuff in case something goes wrong. And then one of your workers dies for a week and you don't know, and your disks fill up and you get a bunch of warnings and now you're losing data. But you don't think about that at the time. Whereas with Kafka, you know ahead of time, I'm going to be storing a week's worth of data, so I need to have enough disk to do that. There's probably other problems, but I didn't think about them. Questions now at the end. Yeah?
They had this something mentioned recently about what do they call it, Kafka pipelines, or like the processing. Was it streaming? Kafka streams?
Yeah.
An addition of like processing part to Kafka.
Oh, I haven't looked into that.
Me neither. It's actual question.
Yeah.
Regarding the partitioning, so are there any common strategies to ensure that your partitions are properly evenly distributed, like the amount of data that each partition gets?
I mean, by and large, my understanding is that most people pick random as their partitioning strategy. There are definitely worst cases there because it's random, but it's so easy to write, and your producer just has to be like, okay, what are the partitions? There are 12 of them? Great, pick a number from 1 to 10, 12, and then I just push to it. Which is like even-ish in the average case. Other than that, no. Like anything that you want to be more, if you don't care about what data ends up on which partition, anything that you want to be more level than that, you're going to need your producers to have a lot more data about what your Kafka producers are producing, or like what your consumers are consuming, or like load stats of your brokers or something. And most people don't bother. That's the answer. Yeah.
Is it possible for like a given topic to kind of, if you wanted to keep it around, to take like a chunk of old offsets and put them into some sort of long-term archive?
Oh yeah, absolutely. Actually, so I work at Shopify. We use Kafka, and in fact, we have a Hadoop cluster that has every message we've ever produced in HDFS. We just do. I don't even know how they're implementing it. It might be a consumer that just writes to the file system. It might be something more basic than that. But yes, at the very worst, you can have a consumer that pulls off every message that's produced and puts it in a forever data store. Absolutely, yeah.
But
yes.
So, but there is something built into Kafka as well, or is you have to kind of write your own?
Like you could just sit your if you want to have enough disk on your Kafka brokers that you just set your retention policy to never delete anything. That's built into Kafka, but your file system will grow unboundedly. In terms of like archiving to a system that isn't the disk, I don't know if Kafka has something built in for doing that beyond just your own ruled consumers. It's even possible that, I mean, like other people have probably written consumers. If that's not the case, you can still pull something kind of off the shelf. But I'm not aware, but that doesn't mean it's not there. This is not my area. Yeah.
Are the petitions, you said they're like a file on disk?
Yeah.
Are they a single file or are they sharded into?
The partitions?
Or sorry.
Or
the logs.
A single partition? Or multiple? Or are you saying? So I believe that each partition file is, I think it's a split file. I think, like log rotation style. When it gets this big, it's now like this is file 1 of partition something, and it like moves on to the next one. I think, but I'm not really confident in that. It might be 1 file per partition. It definitely isn't 1 file per broker. It's definitely 1 file per partition at least, maybe multiple files per partition, subject to time.
Right, because you said it was a syscall to append.
Yeah.
But
Yeah.
I don't know if there's a clean syscall to remove the beginning of the file.
Truncate.
Truncate?
Yeah. But I don't know if that's what it's using for the retention. It might actually be scanning through, because depending on what your retention policy is, it either has to keep that index as it's going, or it has to then like look at when it comes reclamation time. Be like, okay, I'm just going to drop messages off the front until I find one that does not satisfy whatever condition is that I'm doing.
But if it's doing multiple files and you do time-based retention, it could actually delete by modified time, which would be awesome.
Right, yeah, you could just dump a whole file, yeah. And like in terms of the offsets, you know, if you're storing multiple files, you could, you know, if someone asks for this offset, you're like, great, I don't even have to look at that file. You just want this chunk from here to here. But I don't know if that's actually what they're doing, or if they're just doing a single really big file. I don't think this runs on Windows fat file systems, so it shouldn't be a problem if it's one big file. Other things? Going once? Twice? Okay.